The next invite talk is Professor Manoranjan Mishra. He is from Department of Mathematics, IIT Ropar. I think Sir is available online. Now I request one of my students, Sucharita, to speak a few words about Professor Mishra. Over to Sucharita.
Thank you, sir. I'm grateful to get an opportunity to speak a few words about Professor Manoranjan Mishra. Professor Mishra have graduated from Utkal University in 1994 and post-graduated from Berhampur University in 1996. He obtained his doctoral degree from Indian Institute of Science, Bangalore in 2004. Then he continued his postdoctoral studies at INLN University of Nice, Sofia, Antipolis, France, and Université Libre de Bruxelles, Brussels. He is a research fellow of Alexander van Humboldt Foundation at Institute of Fluid Mechanics, Germany, and FNRS, Brussels. At present, he is working as associate professor in Indian Institute of Technology, Ropar, since 2010. He has a huge contribution to the field of fluid mechanics with over more than 75 research papers and over more than 1200 citations. Now, I would like to request Professor Mishra to deliver his talk on reaction-induced instability patterns in a porous media flow. Over to Professor Mishra.
Okay. Is it audible? Do you hear me? Do you hear me?
Yes, sir. Yes, sir.
Some noise is happening. Noise.
Noise? From my side?
From your side.
Okay.
Now it's okay.
Okay.
Is it okay? Is it clear? Okay. Coming from
Just 1 minute.
Okay. Is it audible now?
Yeah, it is audible. Okay.
So maybe. Is it clear? Is it audible from?
Yes, sir. Yes, sir. You can start.
So, many professors and Dr. Sahu to invite me for this meeting, and it is quite late. I was waiting for some time, so it's nice to participate in the Odisha Mathematical Society annual meeting. I'm really delighted to present my talk in front of many people. I see that my teacher, Professor Ponda, is there. Tarini sir, thanks. I could see you are there to listen, and he had taught me the fluid mechanics, and I had contributed very little now, as of now. So I explain everything physical problem, because I've heard so many things about the data science, but I will explain some concept of like, just a minute. Yeah. So my title of the talk, you can see that something is reaction, something is instability and patterns and a porous media. So this is my institute, our institute IIT Ropar. I welcome all of you to visit. I'll be glad to host you anytime. So before starting my talk, let me thank my collaborators, my students, my PhD students, Bandita Sadanand, who is a faculty now in Gandhinagar, Chinar, who is a postdoc Belgium, and Professor Chen and Professor Dewitt, Professor Martin. These are my collaborators. They continuously work. I continuously work with them, developing some of the concepts in the fluid mechanics in the porous media flow. So before starting, I'll just introduce instability actually, and what is the hydrodynamic instability. See, any instability you may be knowing, many of you who are working in differential equation or other concept, other subjects, they will be knowing that it's unstable. That means some disturbance, if you do human disturbance, small disturbance, it amplify. The system is unstable. When the system will amplify, then you see that it will stop here and it will just come back to the same position. It's stable and it's unstable. There are so many other kind of instability. I'm just giving a layman instability style patterns. So in the hydrodynamic situation, in the fluid dynamics situation, in the very since long time, 19th century, 20th century, these are the pioneers who had introduced the concept of some systems which are unstable and stable. So it's Helmholtz, Lord Kelvin, Lord Larrey, Reynolds, and G.I. Taylor of late the pioneer of the 20th century. And with their name, there are so many patterns you can see instability. So there is called Chapman-Taylor instability. There is called Rayleigh-Taylor instability. There is called Kelvin instability. So you see this, you are seeing almost everywhere from your kitchen to your bathroom to your cloudy sky. This is a cloudy sky. You can see the instability patterns, how the clouds are forming. And there are small trees, and you can see whatever you just look at in your eyes and in your wall painting, everywhere you see, you will find a lot of patterns. And those patterns, but some form of some instability. It could be from the instability. And these patterns, you can see that here, some heavy is lying over a light fluid. So heavy is pushing through the light. So this kind of patterns comes. This sky is because of the density dependence between the clouds and the shear and the flow. That's why this kind of pattern comes. Here is kind of a viscosity, which I will be focusing more in my talk. And then the other concept is called Rayleigh-Bernard. If you just hit your pan kitchen, you will see a lot of patches and this is called the Bernard convection. Then there are Taylor-Coate flow when you rotate something, and there are Faraday instability, which is vibrating surfaces. So many instability patterns in our art. I will be focusing basically on a small concept called viscous fingering instability. So this kind of instability, you can see nicely patterns forming. So this is nothing but a less viscous fluid is the left side and high viscous fluid the right side. So less viscous fluid is displacing high viscous fluid, you will see such kind of random, some chaotic, some patterns forms. So here it is kind of a rectilinear we call, that means just kind of a XY domain, and then coordinates here it is a flow is in the radial direction, like something in the center is pushing towards the outskirts of the radially. So it's kind of radial displacement, it is a rectilinear displacement. So this is due to the viscosity differences from less to high. So this is called viscous fingering instability. So in the 80s, in 1986-87, Lord Homsey was at that time in Stanford. He introduced this concept. And before to that, I explained in a simple pipe flow how the viscosity can play a role, and that is called Chapman-Taylor instability. But here it is in the porous media. I'll back details, but look at if I reverse the situation. If I reverse the situation for the high viscous to less viscous. So high viscous is pushing less viscous. So this is kind of a pattern which is just a simple mixing. Just two miscible fluid is getting mixed. So this is stable. So I mean stable means you see that all the situations are very smooth, no disturbance, and uniform, and the growth is proper, and we know the determine the growth. So this is how the stable situation and this is the unstable situation. So what are the things applied? Why do we need to study? This is a long, almost every you look applications, you can see this kind of patterns. So the big problem is the enhanced oil recovery. So when water getting companies, the oil industry, they recover the oil. If we can recover the complete oil, I don't think we'll spend so much on this per now and per liter the oil. So I think it will be very, very cheap. Other oil economy and other things, but we will have plenty of oil. But plenty of oils are we are unable to recover the oil from the ground because the oils, if I'm pushing some gas, some water, water is pushing to the oil, then we get, this is a, you can see this is a input, and there is a production well with the oil. So we push water, polymer, gas, so that oil is getting pushed and then oil is getting extracted. But there are so much of oil. This is the production well will be here or here or here, somewhere. So some oil will come, but some of the oils are, if the yellow is the gas and blue is the oil, then a lot of blues are already gas region. So many oils are not being recovered. So then the big research evolves. So the way you can make the front is more smooth or more stable, not more chaotic, so that more oil will become. So this is how the problem actually. So this is how polymer flooding. There are so many floodings, and that's what our aim is, to give the solution to the oil industry. So then there are all pharmaceutical industry. Now a lot of vaccine is coming. You can see that the pharmaceutical industry is a big important concept. So they do a lot of separation. They should have, all medicines should have the proper component, proper content of the chemical, of the solutions, of the salts. So how do they know that, okay, how much contents are there or not, properly killed or not? And so there are so many medicines like our insulin. This is a big separation process actually. So this is a chromatography processes in the large scale processes. So due to the viscosity difference between the chemicals, so there are some pattern forms, and that patterns actually doesn't help a proper separation. So to help this proper separation, the chemical industry people, pharmaceutical industry people should know why it is happening. And this aspect are not known actually. These chemical industry people, they know how to manage. They can make a longer column and different chemicals, but they were ignorant actually. Our group actually, myself and my other collaborator from Belgium and France, we were the first people to explain that something happens actually in this industry. So we propose the model as well as a lot of solution techniques for this kind of industry. So there is another application called carbon dioxide. A lot of industries producing a lot of carbon dioxide. So carbon dioxide, we are green evolution. We want green transport industry, green industrial development, so everything green, so that we'll reduce the carbon dioxide. One of the problem of the carbon dioxide is how to we store, or how to we take it and properly store it, because that will come automatically. It will come, but can we store? Can we use it for differently? Can we help it for the different energy procedure? Yes, carbon dioxide can be helped to oil industry to extract oils also from the earth. So there are so many carbon dioxide sequestration problems. So fluid dynamic people and mathematics people are trying to support and help how to store, where to store, which place to store. So these are the last 10 years, 15 years, it's a big research in this area. So there is a patterns and because of viscosity and density, so we are interested in that. Then we do experiments. People do experiments. So when they do experiment, there are some 2 glass plates, and sometimes you can do a porous media experiment, but real world porous media experiment is difficult sometimes. But from mathematical scale or laboratory scale to do experiment, people put Hellicer cell. What is a Hellicer cell? Hellicer cell is kind of a 2 glass plate combined, attached to each other. So like 2 glass plate is just joined to each other, and then you push a fluid, and then see the patterns and see the transport phenomena between the 2 glass plates. So that means the basic is that there is a thin gap between the 2 plates, thin gap. Okay. So with the thin gap, that means this mimics the porous media flow. Why? So I'll come back to the model. So you can see that I do some experiment also. So you can see my experimental lab and my students have given me this video. So we could see that how the patterns are forming. So then my collaborator from Japan, he produced such kind of pattern. So we analyze those kind of pattern and try to simulate and model it. What is the model phenomena? I'm coming to mathematics now. So in the modeling, we have an incompressible flow because we take the liquid as incompressible, some various chemicals. Then we have a Darcy law. This is a very simple linear transport equation, which is called Darcy law. It's a porous media flow. I am not talking about complicated porous media flow. I'll be talking about a simple Darcy flow. So that's why, because it's a packed porous media and there's a Hellicer cell. So that's what the main is, Hellicer soil to the porous medium. Then we have the fluid. I have a miscible fluid. So one component fluid. So since we have a one component fluid, we have a simple convection diffusion equations of energy equation. So it's a simple mass balance equation. This is a kind of a Navier-Stokes equation, but in the energy form, in the mass, in the concentration form. And this Darcy law actually comes from the Navier-Stokes equation when you assume a lot of assumptions from the linearized flow, low Reynolds number, and one dimension is not there. So on time, there is no time dependent flow. It's a Darcy flow. So porous pressure gradient is directly proportional to the flow velocity. What is the beauty here? Why do we study? What is the complication here? The main problem here is the viscosity. This is my complication in the work here. So it's a if you make it this is a 2-dimensional, it is a 2x2 system, then 3 equation, then it's another 5 equations, so 5 unknowns, velocity 2 component, pressure another component, 3 component, then concentration is 1 component, 4 component, then another component is the viscosity. Viscosity is depending on concentration. So then everything is coupled now. It's a completely coupled, not one side coupled. It's a fully coupled. If my viscosity is constant, then it will be one side coupled. Because I get the velocity, then I get the velocity, then I put the velocity into the here, then I will solve it. So one side coupled, but it's a 2-side coupled. So this is what Homsey started in 86 and 88. Then we developed further. But there are so many people developed, but our contribution is very much there. So this both papers, my contribution. So it's let's say one interface. What happens to one interface? What happens to 2 interfaces? Look at. When we have one interface, then less viscous pushing, high viscous, we have a patterns. When we have 2 interface, depending on mu1 less than mu2 or mu2 less than mu1. If mu1 less than mu2, pattern will be forming here. If mu2 is less than mu1, pattern will be forming here. So this is how we have understood, we have analyzed, we have explained that which are the practical situations where we can contribute. Okay, I'm coming back to a very simple situation. I'm not come back to my title yet. That what is the chemical reaction is playing a role. Before chemical reaction, I'll explain one model. Then I'll go to chemical model and complete it. So the challenge is that can we control the pattern? Can we control this pattern? That is the main challenge of all over world. Okay. So we have proposed a pattern to control. I am now doing more on the radial, radial flows. Okay, because I do experiment in radial. Rectilinear experiment is difficult, so I am doing radial experiment. So I am more bothered on radial. So if I have a source flow, if I have a singularity here, I will just push the fluid as I showed you in the experiment in the various here when I showed you that how we are doing here kind of things, source flow. Okay. So if I go back to my model here, so I'll tell that, okay, this is the source flow, everything is known from there. Then now I come back to my new model, I will not put source. My source can be finite source. This is what we did a problem. When we did this problem, we have a finite source now. Look at finite source now. If a finite source, the same model, we have the all the model equations are the incompressibility. Then we do a Peclet number formulation. So that Peclet number is the balance of the kind of a non-dimensional number. If somebody does not know anything, then it's a non-dimensional number where if my Peclet number is high or less, then if I go back to this simple Peclet number is much higher, then I'll not have this nonlinear term. Okay, I will have difficulties because Peclet number is not small, then I will have a convection diffusion. So this diffusion term will play a role, this convection term will play a role, nonlinearity term will play a role, and a transient term will play a role. So this is each term of the differential equation. We need to understand what they contribute to the dynamics. And then with the initial condition. This is my initial condition. But this is my initial condition and boundary conditions are, I will tell that, okay, no flux. That means all the gradient. I will not have any, there is no flux is coming, so the Neumann boundary condition, you can think. Gradient of the velocity, del C by del X is not equal to 0. Is equal to 0, sorry, a Neumann boundary condition. So, first I will explain the nonlinear simulation. I'll come back to the can I do anything analytical? So, when we do this numerical simulation, no need to bother much, but we have a simple nonlinear system. When we have a nonlinear system, we have to find a way to do. So, there are so many methods. I follow a simple method called finite difference and a compact finite difference. Okay, there are challenges of various methods. I will not go to the method. I'll just tell that we follow a method and explain the method. So my velocity here, if I have a source condition, finite, my velocity is external component plus a potential component. Potential component means my linear velocity. Then this is the nonlinear velocity. So this linear velocity I know from this system of equation. So this is nothing but a singular equation. There is a singularity involved here because there is a singularity flow. How do I reduce the singularity? I can reduce the singularity through a assumption. I will put that some Gaussian source so that x and y equal to 0. Through this kind of singularity, by the time xy goes to 0 here, exponential will go much faster. That means I will not reach the completely x and y 0, 0. I can avoid the singularity. I will have a finite time before going to singularity. That's what Gaussian source will. It was by a group and we have utilized. Then I followed a method, a kind of a stream function vorticity. That means kind of a formulation so that we can reduce the unknowns. Reduce the unknown. We have a vorticity formula. This part computation. This to do finite difference. When you do compact finite, you have a time component. Time component, you do Runge-Kutta. Just integrate to integration. Then take it to the Poisson equation. Poisson equation solved through a spectral method, kind of a Fourier transform method. because it is now Poisson equation, linear equation. So with the spectrum, then combine the velocity from the U, then keep going, keep getting. By doing that, I took the finiteness play an important role. With this finiteness playing an important role, I did a finiteness with a different radius. You can see that if I increase my finiteness initial condition, I have a stable profile. Here it is more unstable than it is more stable. There are so many reasons, okay? So physical reason, you can see that this is more unstable, this is less unstable, I mean. So this is what I did experiment. We did experiment in our lab. You can see that I have a less radius and a higher radius initial condition. You can see that patterns are small patterns. Here it is more unstable. I mean more unstable, it is small, less unstable. So I could capture this clearly by reducing by increasing capture my make more stable. This is what we published recently last year in the fluid mechanics, the common. So I did linear analysis for so for linear stability analysis is very basic concept. You have a linear regime, then you put a linear regime perturbed it and then try to compare it. So we follow a linear and nonlinear regime method. Same things we did. We have a base flow velocity. We have to perturb the concentration and stream function, everything. I'm just perturbing. So following the analytical method, we combine this part we follow from the analytically, this part we follow from the numerically, we combine and then we made a linear stability analysis. When you do a linear stability analysis, how to understand the growth of the system? We have to define the energy amplification. So we have defined the energy amplification through a formula. Just take home messages. When we do dx by dt equal to x, we get exponential growth. Can I find a system cannot have exponential growth? There can be some algebraic growth. So can we find a algebraic growth? This is the challenge. We did that. Okay, following. So we could show clearly that we find that wherever this kind of energy is minimizing, that is the stable point. So whenever energy is growing, that is the unstable part. So it is stabilizing, then instability is coming. So these are the onset of instability, these points. So by justifying in this way, we could convince the people, and we have published. This is a very important work we published by making the linear, nonlinear experiment combined way of the analysis. Anyway, so I'll go to my next problem. So challenging was that I'll take another 2 minutes to complete my next problem because I hope I have the time. Because challenging is that can we suggest any new methodology to get another kind of pattern controlling? You can see that here there is a stable pattern, here there is an unstable pattern. So if the both chemical is same, both fluid is same, it is a stable pattern. If the viscosity is different, then only it is an unstable pattern. But in a small microfluidic situation, you have a small pipette, small pipe, your printing industry, or anything in a small conduit. The challenge is that can you do a better mixing? You can mix your things in your steering, in your tabletop, in your beaker, you can mix a chemical, but in a small pipe, you cannot mix anything. So, can we help in mixing dynamics? Can chemical reaction play a role? Can I induce automatically a system for a mixing? We propose that I can have a chemical changes of the reaction so that it can get mixed. This is with look at now. There are a lot of experiments. I have not done experiment. There are a lot of experiments. People have found this kind of challenge. Can we model it? So for modeling, I followed the same type of equation. I have chemicals A, B, two chemicals reacting and giving a product. So what is the beauty of the mathematics? What the mathematician will look from here? The mathematician will look that I have a convection term, I have a time component, I have a diffusion term. I can have a reaction term. So another nonlinearity. I will use another nonlinearity so that this will help me in my physics. So because this nonlinearity, I could easily create the mixing dynamics. Same procedure. Look at. I have just simple two same chemical. But two same chemical, if it is same viscosity, it will be the stable. But my product, whatever the product is, if there are two products, these are the two chemicals. So some two chemical, you think, because some of you are familiar with chemistry or physics. So two chemicals, some HCl, hydrochloric acid, and some polymer here. Another polymer with the water. So with sodium hydroxide, then they give something like some of the kind of product. If the viscosity, density, yes, it plays a role. So this is what we played. Then we justified, we used the word dynamics, showed that even though there are two chemicals play a role from our nonlinear dynamics, nonlinear mathematics, we showed there are so many nonlinearity plays a role. We can get a stable pattern. Here we can get a stable. Here we have given two nonlinear parameter. This is the chemical reaction number. This is the mobility number. So these are the two number which is driving the flows. I can show this phase diagram. This is a big challenge for us. So we could show this. This one published in 2019 Journal of Fluid Mechanics, which is one of the important journals for our community. This is what I have published now in recently by defining some other kind of physics. We have done some of the linear analysis here and nonlinear simulation here and experimental observation. We showed that we can play a role with the physics and chemistry through the mathematical terminology. Which term is playing a role, which term of the mathematics is playing a role. We can define it. So my conclusion is that I can control the pattern formulation. I can understand what is the mathematical advection term, what is the diffusion term, what is the initial condition, what is the boundary condition, how each terminology of my system of coupled nonlinear equations, we can understand better way from a mathematical point of view and suggest to the engineers and the physicists and chemists, biologists to look for their physical problem and to design something different. Thank you very much.
Thank you, sir. Is there any question from participant side?
Thank you, Professor Mishra. It was an excellent talk. I enjoyed listening to you. Thank you.
Thank you. Thank you. I would like to hear from Professor Panda is there. Professor Tarini sir, are you online? Are you hearing?
I am there.
Oh, okay.
How are you now?
Sir, fine. Sir, namaskar.
After a long time, namaskar.
I'm happy to present before you this opportunity. I have not met you since 25 years, more than.
No. We met each other in Indian Institute of Science, Bangalore.
Yeah, maybe 20s.
Your
20
guide is
years
a friend of mine.
Yeah, 20 years before.